double check it's actually recording. Yes, it is.
Oh, that too, yeah.
And we'll check the amount of space left. We got 42 gigs. We're good to go. All right. And we're going to need it too.
How big are your files usually?
About 1.7 gigabytes or so. But it's really high resolution because it's almost lossless. Almost.
So I was going through the when you have a little reading thing for the binary, and if you go to your and if you like just mess around with the URL, you can get back to your TAP teachers website.
Yeah.
So what used to be 317?
372.
You have a list of all the classes that you used to teach at AR. This clearly is like from like 05.
You mean 370?
No, 317. You have like a 310 and 17 and 317 and 17.
317?
Yeah.
It probably. Oh, it's embedded. It's more of using a AVR design.
Okay. And on American River, you still have that class?
Yeah, we used to have it. The thing is, we have to make sure all our classes articulate with UCs and CSUs. So we're kind of confined by what we can. Because of that, we are confined to what we can teach in these classes.
Why do they get rid of the robotic class?
The robotic class, well, until it actually transfers to a robotic class at a 4-year university, the chances of us actually having enough students, is pretty slim. Yeah. All right. So let's go ahead and get started because you guys have a new homework assignment. So I'll do the usual annoying thing of giving you the new homework assignment first, and then we'll go back and talk about how to do it. Because I think this motivates people a little bit more. All right. So here's a new homework assignment. It's not the same as last year. So if you want to watch how we did a homework assignment from last year, that's fine, not a problem. It's probably a good information to begin with. So yours is called a 2x2-bit speedy adder, okay? But we'll just call it a 4-bit adder, okay? So this logic sim design should have 8 input pins, 4 pins representing 4 bits of a number x, 4 pins to represent the 4 bits of the other number y. Label the input pins x0, x1, x2, x3 for the first number, y1, y2, y3, and y0, y1, y2, and y3 for the second number. So those are the input pins. x0 and y0 are the least significant bits of the input. x3 and y3 are the most significant bits. So do we have any questions about this paragraph? I'm just going to highlight this portion here to see if you guys have any questions. Yep.
So you want 2 bits inputs and 2 bits though?
No, it's 2x2, which means you are going to make a 2-bit adder, but by stacking the 2-bit adders, you can make a 4-bit adder. Okay, so that's what it means, 2x2. Okay. All right. So as far as output pins are concerned, there are 5 output pins. The 5 output pins are, yeah, that would work. So the 5 output pins are Z0, Z1, Z2, and Z3 are the 4 bits of the sum, and then C is the final carry bit. I actually have to make one little change to the description. So I'm going to switch into edit mode so I can actually change it while I'm reading it. Because that's one little thing I forgot that we have to change. Okay, there we go. And I can just zoom out so this way we can see the entire thing. Okay. Okay, so the first restriction you might want to observe is you have a gate use restriction. You can only use AND gates and OR gates. Okay, no other gates, no exclusive OR, no NAND, no NOR, that sort of thing. Okay, so you can only use AND gates and OR gates. Okay, and there are further restrictions also, so I'm going to talk about that when we get there. Okay, and the gate can only have a width of 1 bit. Okay, so there's a width attribute to a gate, and it can only be 1. Okay, it actually makes sense. Okay, if you make it multiple bit width, it actually doesn't work. So here's the structural restriction. The structural restriction is you have to make a new circuit, okay? So instead of the main circuit in Logic Sim, you have to make a new one and call that new one add 2 because it's really a 2-bit adder, okay? It will add 2 bits. It will add 2 bits from one number to 2 bits from another number, and giving you the result of 2 bits and an extra carry. So those are the pins. So this is where I made that mistake. Okay, so there actually turned out to be one more input pin. So one input bit for a carry in from possibly another adder, because without this carry in, you won't be able to make a bigger adder out of this. Okay. All right. So structurally, this circuit must fit the following general format. At the top level, you can only have disjunction operations. So if you look at the operations overall, that means the last operation should be a logical OR. Now, how many terms can you feed to this logical OR? As many as necessary. Okay. You can have 2 if that's all you need. You can have 4 if that is all you need. You can have 6 if that is all you need. Any number. Okay. Is that okay? So the overall equation is going to look like this. Okay, something something, or something something, or something something, and so on. And you can have as many ORs as you want at the top level. Is that okay or not? Okay. So then the next question is, what about each term in the disjunction? What can it be? Now this is a little bit more restrictive because each term of the disjunction operation is a conjunction, which means inside these parentheses, you got something and something and something and something. But the further restriction is what can you use for these individual spots? They can either refer to an input pin, okay, or the inverted or the negative form of an input pin. So this can be x0, can be the carry in, okay, the carry in, we call it C in for carry in, can be the negation of an input pin. So we can have a not, okay, since I'm using C notation, I'll just be consistent. It can be a not y0, okay, that's okay, okay? Or, you can also have just another simple one, which is just y1. So this term can break out into a conjunction. Each item in the conjunction can either be an input pin directly or the negated form of an input pin. But that's the restriction. Is that okay? So when you look at a picture of your circuit, it's going to look like this, okay? When you look at the picture, you don't have to use a particular orientation, so if you want your output to be up or to the right-hand side, it's okay, or down, that's up to you to decide. But the overall speaking, you have a huge OR gate. Well, it doesn't have to be huge, and it sends something out to an output pin. Each input to this OR gate is the result of an AND gate. So I'm just using a very simple example here. It has 3 AND gates feeding into the OR gate. And then each input to the AND gate has to be coming from an input pin. So it can be straight from an input pin. It can be the negative form of an input pin. Okay? If you feel that it doesn't need a particular input pin, don't use it. Okay? You don't have to use all the input pins for every single gate. Okay? So you can have another one here that only goes into here and goes into here, non-negated, and then this one is only going into here, negated. So this is the kind of circuit that you're making. Is that okay? Does everybody understand the restrictions? So this also means that there are degenerated forms of this kind of equation, because what if your conjunction term here only has one single thing, which is a pin? Well, if that is the case, okay, if that really is what you need, you can feed a pin directly into the OR gate. That's okay, because a single term is a conjunction that is just ending with true. Okay, so you can quite easily turn it into actually a conjunction, but it's trivial. Yep.
So OR in can be negated too, right?
No, the input into the OR cannot be negated.
But you just
Correct. This is an exception because this is coming straight from an input pin. If it's coming straight from an input pin, it can be negated, but if not, it cannot be. So if you don't want to do with this special rule and you only have one single pin, I would just do something like this. Just make an AND gate out of this whole thing and have two negated bubbles and feed that here. So that will fit the requirement. Is that okay? All right. All right. So this is the general structural requirement of the add to component. So I have some examples here. I expressed everything in LaTeX, so I have to switch back into the display mode just to get this part displayed. So just hold on a second here. Let me show the content. Alrighty, there we go. Okay. So for example, this is okay. This expression meets all the requirements because, okay, let me magnify it a little bit closer. There we go. So this expression here meets all the requirements because the overall operation is an OR. You remember the plus means OR in logic. And then each term is a conjunction because remember your multiplication is used as conjunction when we're talking about logic. So this is okay because inside each term can be negated. So x1 is negated, y1 is negated in the first term, and then y0, y1 are negated in the second term. So that's perfectly okay, not a problem. And as I mentioned a little bit earlier, you can have degenerated expressions. So x0 by itself meets this requirement because there's only one single pin, okay, out of the entire equation. If you want to force it into this format, it's pretty easy, but there's no point in doing that, okay? So x1 or the negative form of x0 meets the requirement. x1 bar, which is the negative form of x1, meets the requirement as well. This one single thing, which is a single conjunction, is okay as well, okay? In other words, if all you need is just an AND gate with inputs from the input pins or the negated input pins, and that's all you need, you don't need this OR gate here because you can quite easily just feed the same thing into two pins of an OR gate, so it doesn't really change the meaning. Okay. As I said a little bit earlier, you can feed pins or inverted pins, negated pins directly into the OR gate. Okay, because it's easy to turn this into the format that I want. The following, these are not okay because because the overall operation of this expression is an AND gate, not an OR gate anymore, and that by itself is not good. Okay, because when you look at the AND, one term of the AND is an OR, so that's not okay because we have an OR before an AND gate in this example. The second one is the same way too, okay, because we perform the OR first, and then we perform the final AND, and that's not the right order that I want. Yep.
Why are we ending with 4?
Huh?
Why are we ending with 4?
Because this is called a DNF or disjunctive normal form. When you express equations or expressions like this in DNF, it makes it a lot easier to implement in logic, in actual gates and transistors. Not sure whether that answered the question. No? Okay.
Because we're getting one output here, right? Like,
Yes.
But our output's not going to be a number.
It is a number in the individual bits. It's going to be a number. So your circuit,
Four outputs from the OR?
no, but you have multiple OR gates as outputs.
Okay.
Each bit is going to be represented by like that.
Okay, so your circuit is going to look, just for the add to, it's going to look like
So
this.
that's just a set of one bit.
Okay, I can give you some examples later on. Let me finish the description of the homework, then I'll give
I
you
think I got
an
it.
example. Well, I'm going to do it anyway, so. So your main design is going to utilize the add to components. In other words, the component add to is a class, okay? In object-oriented programming terms, add to is a class. So you're going to instantiate X number of these things, okay, and use them together to make the overall circuit. You will also need a constant 0 because the input to one of the carry in has to be a 0 to begin with. So this is not entirely true. Your main circuit can only make use of pins, wires, and the add to components, but you also need a constant 0, okay, somewhere along this line. So I'm gonna change the text again just to reflect that, because I don't want you guys to be going like, okay, what about this 0 here? Now, you don't really need a 0 because you can actually make a 0, but then it won't meet the requirements of the homework assignment either. So I'm just going to allow you guys to use a constant 0. So the main design can only use constants, pins, wires, and the add to components. So that will do it. Okay, save. You have 1 week to do this homework assignment. Even though next Monday is a holiday, next Tuesday is not a holiday. So we are meeting next Tuesday. All right, so getting back to where I left off here. So the tip is to express each output pin as a disjunctive normal form, and I strongly recommend anyone who does not fully understand what I'm talking about here to right-click on this link and just to read what is a disjunctive normal form. It's a Wikipedia page. It's not difficult to read. It's just a restriction of the structure of the gates. So what you need to do with this homework assignment is to understand the algebra of the Boolean algebra. In Boolean algebra, we have the usual stuff. The distributive law works pretty much the same way. There's also the reversed form of the distributive law. In other words, AB, the whole thing plus C, is the same thing as A plus C in parentheses times B plus C in parentheses. Let me just write it out here. It works in Boolean algebra, but not in normal arithmetic algebra. So let's see. We want to go to mouse pad. Okay. So what I'm claiming is this. In logic, okay, you can do this. You can say AB, which is A and B, or C. This is really the same thing as A or C and A or B. B or C. Now in math, in normal arithmetics, this doesn't work, okay? But in logic, I claim that it works. So when I claim something, what do? What do you ask?
Challenge.
You challenge it and go like, okay, is that really the case? Can we prove that is the case? Now, because this is Boolean algebra, everything is easy to prove. Easy peasy, because you can prove it by a truth table, okay? So, which is, in a way, brute force, but, if it works, it works. So you have 3 input columns, A, B, and C, so I'm just going through the proof here. So you have 0, 0, 0, 0, 1, 1, 1, 1 for the first column. Then the second one, this is just the way I like to do it. You don't have to do it exactly this way. But as long as you have all 8 combinations of zeros and ones, it's fine. But this is just the way that I like to do it, because there's a certain pattern to it, and it's hard for me to miss something this way. Okay, there we go. So, what is A and B or C in this case? That's a pretty easy one. 0. What about this one? It's a 1. In fact, all the ones with a 1 in C are automatically 1s already, so I can just fill all those in. That's pretty easy. Okay, what about this one?
0.
0, because we need AB to be both 1s in order for the output to be a 1, like this one.
And the last one. What's the last one?
Yeah? I did the last one already.
Yeah, the last one.
A, B, that's 1, plus C, that's 2.
What?
It's not plus.
No, that plus means disjunction.
Oh,
There's no 2.
I know.
Yeah. Well, you have to get used to it, unless you do not intend to transfer. Then you don't need this class to begin with, right? Okay, what about this one here? A or C, and the whole thing, and B or C. Wow, that's an easy one, right? What about this one?
1, 1.
Okay, or C. Well, C is
It's a 1 because C is on both sides. So, whatever and or 1 is a 1. Okay, what about this one?
That's false. No, it's true.
Is a false. What about this one?
One's true.
True. And what about this one? False.
True.
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 True. And the last one obviously is true. Okay, so we can observe that these two columns are exactly the same. Okay? So with Boolean algebra, this is all you need to establish the equivalency between two expressions. If the two expressions involving the same variables are all the same across all the input terms, then this expression and this expression are the same. Okay? That's how easy to prove equivalency in Boolean algebra. It's not that easy in arithmetic, right? But in Boolean algebra, because you are confined to only two possible values per variable, we can do this. Is that okay? So you might need this one, I'm not really sure, but you might need to use this particular distributed law, which does not exist in normal algebra. Okay, and the other one is De Morgan's law. So De Morgan's law says if you have an overall negation applied to A or B, it is really the same thing as applying the negation to A and the negation to B individually, but then you have to change the disjunction into a conjunction. Okay, and the reverse of that works as well, which means over here we have the negation of the entire conjunction, okay, with A and B inside. But it's the same thing as applying the negation to A and B individually and then change the conjunction into a disjunction. That works as well. Okay. Now these are all just claims. If you want to prove that these are all true, that De Morgan's law works, you can make your own truth table, go through each and every single one of these and prove that it works. And these are a whole lot easier because you only got two independent variables, which means you only got 4 rows, and it's pretty easy to finish. Yep.
These are, because I'm normally used to seeing different, these are the exact same thing as like A plus B in parentheses and a negation on the outside.
Yep. Yep. But this is the more compact way to express it. Yep. Okay. You might also find simplification rules to be useful because sometimes you just say, oh, if I have that, this is the same thing as the other one. So obviously, not A and A is false, okay? Because one of them has to be false. So the conjunction has to be false. A and 1 is A because 1 is the true is the identity of conjunction. I'm talking about the second item here. A and 0 is a 0, okay? Because anything and false is false. And then we have the commutative rule, which is AB equals to BA. A and B is B and A. A or B is B or A. With disjunction, the identity is 0 or false because anything or false is that something originally. Anything or true is true. Not A or A is true because one of them has to be true, and if you have at least one side being true, the disjunction is true. And then we have this one here, which is reversing the distribution, okay? And as a result, we can say if you have a A term here, and it is ORing with something that is A and then something else, you can just simplify the whole thing to just A. So that can help you, kind of compactify the terms so you won't end up with a gazillion gates. Is that okay? So this is kind of something new to you, Boolean algebra, so you kind of have to use Boolean algebra in this homework assignment, okay? And how I will grade and test your homework assignment is I'm not going to test it with 256 possible test cases, okay? Because that's just way too much for me to do it by hand, okay? But I will select a few representative cases to test your design. In order to get any score out of the design, it must meet all the specifications, the interface, the pins, how you use the gates, and structurally how you structure the gates. Given all the specifications are met, the design will be tested with the test cases. So depending on how many test cases work in your design, you will get a score proportional to the number of test cases that your design works successfully. Yep.
So if it works but looks like garbage, it's still okay?
Say again?
If it works, but looks like garbage, it's still okay.
I will still have to be able to find the input pins to test your design.
Yeah, as long as it works.
As long as it works. Yep. And you will find that, if your design is really convoluted and stuff like that, you will find it difficult to debug it yourself. It's like writing, code in C and C++ with no indentation.
All on one.
When I see homework submissions like that, what pops up in my mind is, okay, somebody copy this from somebody else in a hurry, and say, oh, we don't need spaces here, because it's a really clear indication it's copied, okay, especially if it works.
Or they just want to make it.
Oh, this brings up one interesting one. A long time ago, I taught Pascal, which is the predecessor of cisp310. And one of the students turned in as a final project, which was kind of complicated. It's got lots of logic and stuff like that. The use of structures, or what you know as structures. In Pascal, it's called records. Okay, so it's a pretty complicated program, and this guy turned in a program that did not even compile. And what it was missing was a single semicolon. Otherwise, it compiled and worked perfectly. Okay, so what do I know about this? You probably copied it from somebody else. Because there's no other way that people can write programs like this. I can understand programs that do not work 100%. But there are certain test cases, boundary cases that it won't catch. But the program compiles, it works for certain cases. I can understand that. But a perfectly written program that is missing a semicolon, and I asked the guy, well, in order for you to get some score, you have to fix it first, okay? So I was watching him fix the program. He had absolutely no idea of how to fix it. He was just staring at the program going.
Not his day.
Yeah.
It was not his day.
No, but with a mentality like that, there are days, there'll be like days like that in his future as well. Yep. All right. So, okay, this is the other class. Don't worry. All right. So what we need to know is how to do the transformation thing, so that we can coerce everything into the D and F format. Okay, so that's the first thing I'm going to do, is to show you guys, how to do it in general. May or may not have anything to do with your homework. Okay, so keep that in mind. Probably not, because I'm just randomly picking cases. Okay, so we'll use the video camera here. Now we have sound. But, if you are here physically, I think the sound is useful, but not as useful as just, what is on the screen. Okay, the details are actually what is on the screen. Most of the time I say things wrong anyway. I look at my own notes and I say, x2, y2 is actually x1 and y0, right? All right. So, but the video part is recorded from the beginning of the class, and I think that's the more important part. Okay, so so let's hook up these things. And many years ago, I was only able to do audio recording without the video. Just technically, I could not record a video. I just did not have the technology to do that. Okay, so for the first one, x just goes to the input of the first half adder, y goes to the other input of the half adder, and then the output of this. Okay, let me see if I can remember how to do that. So the output of this just goes to one of the input of the half adder. The carry in goes to the other. Yeah, that's right.
Yeah, that's right.
Okay, so the carry out of the individual half adders have to go through a disjunction before going out as C out. So the result, the overall result is just the result of the full adder. There we go. And then these two carries need a disjunction, like that. Okay, and we'll feed this one over here, and we'll feed the other one over here, and then this becomes my overall carry out for the full adder. So now I have a full adder circuit done. I know some of you would go like, I can make this look a lot nicer, and I don't doubt it at all. Okay, so you guys can make it look as nice as you can. But this probably is functional. I'll check it, okay? So right now it's saying, if carry in is 0, x is 0, y is 0, then the result is a 0, and there's no carry out. Looks good to me. 1 plus 0 with no carry in has an output of 0, and has a result of 0 and no carry out. Okay, sounds good to me. 1 plus 1 has a carry out of 1, and the result is 0. Sounds good to me. 1 plus 1 with a carry in of 1 will end up with a 1 as the result and a carry out of 1. Sounds good to me. There are 8 individual test cases here. Okay, so it's not really that hard to test all 8 cases, but if you do test all 8 cases, that means you are sure that the full adder is working before you start to use it as a component. Are we doing okay so far with all these test cases? Okay. All right, so with this done, what I do is I go to FA, right-click on it, and say Edit Circuit Appearance. So you can see it turns it into a chip as well. And this time, because the pins are really close together, I don't have enough spacing to really put the labels. So one thing I can do is to kind of make it a little bit bigger, just so that I have enough spacing between the pins to label the pins. Especially inputs. Oh, this doesn't line up. Come on.
Control Z.
No, it should be able to move. This one moves. So how come this one does not? Oh, the other thing you might notice is when you click a pin, it shows a little picture, like a PIP, a picture-in-picture, to show you which pin in the actual circuit you're referring to. So that's actually very helpful when you're dealing with something that's big and complicated. Yep.
So when we're creating ours, we're supposed to be doing it like this, like making little pieces and then making those pieces into circuits and then using the same
You won't have
pieces over and over.
You won't have small pieces like this, because the small piece that you have is the add to component. Now, if you want to have any sub-component below that level, feel free. Okay, I encourage modular design. So if you think, okay, I can make more individual pieces, that's fine. But the overall design has to fit the hierarchy of there's an OR gate, and then there's a whole bunch of AND gates.
Okay, you say add to, like we're adding just 2 numbers? Is that what add to basically?
Your add to has 2 bits. It's adding 2 bits to 2 bits with a carry in. So the result is 2 bits and it has a carry out. I'll show you what it looks like, okay? Because I just have to finish the full adder first. Okay, so I'm gonna label it here, because I have enough spacing to do that now. So I have X, Y, C in, and then we have R and C out. There we go. Just move things a little bit. Okay. There we go. Looks good enough to me. So go to project again. Oh, by the way, one more thing. Okay, remember to save your design like periodically, because Logisim has a bad habit of crashing. So you should assume most programs will crash. So just have a good habit of saving once in a while. Okay. So this is done. So I go to project again, and this time I'm going to do an add to. Now this is important because this relates to your design. Okay, the actual guts of add to, not so much. But when you look at the overall interface of add to, that's what you need. Okay. Okay, so it's going to have 5 input pins. Okay, so I'm going to do the duplicate here. Control D duplicates, which is an easy way to keep making the same thing over and over again. Okay, so your inputs into your add to circuit is going to be X0, the first bit, X1, the second bit of X, Y0, the first bit or the least significant bit of Y, and Y1, which is the most significant bit of Y, and a carry in, like that. Oops, not SIB, it's C in. Okay, and your output is going to be 3 pins because you have R0 as the least significant bit of the output. You have R1, which is the most significant bit of the output. And then you also have C out, which is the carry out of your 2-bit adder. Okay? Is this part okay? Just defining the input and the output of the 2-bit adder. Any 2-bit adder would need these input and output pins. The only difference is what is inside the adder. Okay? So in my case, I'm going to use the full adder because I'm not doing your homework. So I'm just doing this the slow way using a carry ripple adder as a mechanism. So my design is just going to be using 2 full adders. So I will put one right about here. And you can do all the usual stuff, like selecting the whole bunch and move them a little bit away. Okay, another full adder over here. And that's all I need. Okay, so now I just need to draw the wires. So X goes to X, Y goes to Y. And then only the least significant bit needs a C in. Sorry?
It's about to get ugly.
No, it's not going to be too bad. Okay, X goes to X. I used to lay out circuit boards. And then the C out from the least significant bit goes to the C in of the most significant bit. So this is the result of the least significant bit. This is the result of the most significant bit. And this is the carry out overall. So I wouldn't call this too bad. I mean, it's okay. There are a few wires crossing, but not too bad. And by the way, some of these wires that are crossing, one probably has to be crossing, but the other one does not. In other words, going from Y0 into Y. Okay, let me just point out that one. Okay. Yeah, so this one doesn't need to cross. Okay, so there's a way. Oh my goodness. Okay, because it selected the whole thing. Oh, it doesn't let me select just that.
There, click there.
Oh, okay, fine. Yeah. So now we don't have a cross of that. As I said, I used to design circuit boards. When you design a circuit board, like a actual PCB, you cannot cross wires because so you have to find ways to route around things. Go under, and then go back up again, and do all sorts of things. It's actually a lot of fun. So anyway, you don't have to do this. I'm just showing you, yes, you can, if you are anal about this type of thing, you can actually do that. You can also reposition the components to reduce the overlapping and stuff like that. You can change the orientation, but don't go too crazy about this, okay? All right, so now we have a 2-bit adder, and with a 2-bit adder, there are a lot of test cases. So I'm not going to test every single case. I'll just test some really obvious ones, like 1, 1 plus 0, 1 is going to be 1, 0, 0, okay? So we have 1, 1 as, oops, not this one, 1, 1 as the first number, and then 0, 1 as the second number. I should end up with 1, 0, 0, which is the carry being 1, and then both results being 0, okay? So test the kind of, do your own tests, okay? Find out what cases are the most representative, and then test it. Now, this picture looks so simple as an add 2 component. Yours is going to be ugly. Okay, so don't even expect it to look close to this clean. Yep.
So you did basically our homework assignment, but you did it in a modular kind of way, and we're not supposed to do it that way?
Yours is going to have OR gates and AND gates in this picture. And lots of wires flying around.
We're not going to have chips like this.
You're not going to have chips like that. Because remember, you have to use DNF.
Yeah.
No chips.
I'm not using DNF at all. Yep.
I don't understand exactly how yours is different than ours is supposed to be.
Yours is supposed to be a DNF, which means it has one huge OR gate with a bunch of AND gates feeding into the OR gate. I don't see any AND gates or OR gates here.
So you did something in yours that we're not allowed to do in ours?
Absolutely correct. why would I do your homework?
No, which part? What am I not allowed to do from what you did?
I am showing you how to use LogicSim and how to make a hierarchical design. That's the purpose of this exercise, is for me to show you how to use the tools so that you can make small components, utilize the small components in a bigger component, and so on.
But ours is just all small components, no like combining them. It's
Well,
just a bunch of little things.
you can copy this and this. so you can copy the 5 input pins and the 3 output pins, and that's about it. The inside is all completely different. Yours is going to look ugly.
So our inside will basically look like the very first layer, which is the very first thing you did, just a lot of it.
Yes.
Okay.
Yep.
So on our program, we're gonna have 5 input pins or 7. So here it says that we need it from.
Oh wait, but there's more to this. Okay, this is only an add 2 because remember you have an overall design that is a 4-bit adder, right? This is only the one step. Okay, so in your design you're gonna have to add another circuit, which is your main circuit. Now you don't have to name that the way I do. I'm just going to call it add4 for a 4-bit adder. So in this 4-bit adder, what you're going to do is to utilize your 2-bit adder. Okay, so you're going to put it here. Now I did not even bother to change the names and put labels on it. And so then you need 2 of these and 7 inputs.
So
No, I take it back.
8 inputs.
Yeah, but
8 inputs, correct. Yeah, 4 bits, because you don't have a carry in this case. Yep.
So we are
Yeah, that's what
allowed
the whole thing
to do a modular design, but we're only allowed to break it down into twos.
Yes. So in your case, your add 2 is basically your lowest level design.
Okay.
Okay, because you're not going to use a half adder, you're not going to use a full adder. Because when you look at a half adder, and a full adder, they really do not follow the rules. Okay, especially when you combine them into a full adder, it just doesn't follow the rules anymore. Well, except for one, one actually does follow the rules, but the more complicated ones do not.
You can't use a modular in a modular.
You couldn't like.
Well, if you use a modular in a modular, the question is the overall design only have 2 levels of gates when you look at the add 2?
No.
So yeah, exactly. If it does not only have 2 levels of gates, then it does not fit the description of the homework.
Yeah.
Because the bottom line of the homework is when you look at the add to, every single output pin has to hook up to a disjunction, and then the disjunction hooks up to multiple conjunctions, and then these conjunctions can then hook up to the pins, the input pins, or the negated input pins.
Good times.
At least it's not a 4-bit adder.
Or three,
Yeah,
three.
right.
Okay, trust me on this one. Okay, a 2-bit design is a lot easier compared to a 3-bit design. That one extra bit thing is gonna make it explode.
So if you did create a 2-bit, like you couldn't just like add to your 2-bit to make it a 3-bit, or you have to redesign the whole thing.
Well, when I say a 3-bit design, I mean a 3-bit design that's self-contained and not utilize a smaller component. So it's going to be a lot more complicated.
Yeah.
So like the designs don't build off each other. Basically, that's
Okay.
what I'm saying. Like if you're not using the entire amount of one.
Okay,
like,
just
to make
so
a
I.
whole, then they don't build, the designs of like one doesn't build off the other. Like, it's not like you can design one little part of it and then
He's asking if
You
add
can't
more
do that.
utilities. It's
Be-
more like you
because-
gotta solve the entire problem at once.
Okay, so at this point, we have about 5 minutes left. So what I want to do is to relate what you're doing with what is the main point of this whole thing. Okay, so if you look at the design that I did, okay, which is this one here, okay, this whole thing is sequential. In other words, the most significant bits won't settle until the least significant bits are done computing. Okay, one particular bit has to propagate in a very sequential manner. Is the carry bit. Okay, so even though the calculations, the gates are all working at the same time, simultaneously, it will change. It will keep changing because until this C out is done, because it's the input into this full adder, the output of this full adder does not mean anything. But until this bit is done, then what it feeds into won't really matter, until all of these bits are done. So you have to wait. Okay, if it takes 2 nanoseconds for one full adder to settle down, and you have a 64-bit adder, then you will need 64 times 2, which is 128 nanoseconds for the entire number to settle down to be the correct value. Yep.
So what you're saying is the more of these components that you get, the more
Delay.
the more of a delay you have.
Yep. And that's why Intel does not use this type of design. Because this way, if you do it like this, and you have a 64-bit adder, it's going to take up a lot of time to finish the addition. Yep.
And our design is meant to circumvent that.
Your design, which is kind of based on this picture here, you are making these huge terms. But nonetheless, if you look at the most complicated, pin, it is still only how many. This is an output pin. These are all input pins. Okay. So how many levels of gates do we have, even when you consider the most complicated, output pin? 2 levels. Okay. If you want to count negation, up maybe 3. Okay. The complexity is coming from, we have tons of terms here, to make up this, but they are all computing at the same time. So the propagational delay to get the actual result is no more than just 3 levels of gates, regardless of the actual width of your adder. Now, when you add one more bit to a 2-bit adder, it significantly increases the complexity of this picture. But nonetheless, the structure of the picture does not change. You are just making more and more AND gates here to merge into that big, huge OR gate. But you're still only looking at 3 levels of gate propagation. In other words, the amount of time to come up with a 64-bit sum will still be the propagational delay of 3 gates. Now, when you look at bit 63, no human can work on that. So Intel has tools to automatically generate these things. Okay, but that's the whole point. Okay, from the perspective of Intel, performance is important. So they have to do it using this particular way. Instead of using full adders, wait for the carry bit of one full adder to settle, then work on the second one, wait for this to settle to work on the third one, and so on. Because if you do it this way, the propagational delay is proportional to the number of bits of the adder. Yep.
Does AMD do the slower way?
Oh no, they all do it the standard way. The standard way of using yeah. No, AMD does not use this way. This is like industry standard. Okay, the only time you encounter something like the one that I demonstrated here is a textbook. This is what we call a typical textbook design of an adder, which nobody uses in industry. So if you want to be ready for industry and be an interview with Intel or some other manufacturer and say, yes, I know practical stuff too. Okay, I understand. They may not ask you to work on bit 64 or 63, in an interview because it will take you months at least, if possible, to do it. But at least if you say, okay, I understand the difference between the designs. If you have carried ripple, able to be proportional to the number of bits, but when you do it the other way, it is a constant delay. Okay, you only have 3 gate propagation time. Then the interviewer knows, okay, you know practical terms. You know what is practical in industry, and not just textbook cases like that. Yep.
Can this be applied to like the big O notation? That's the worst case, and this is.
There is. The big O in this case would apply to the number of gates that you need, but it does explode, exponentially, because when you add one more bit, then you have to take all the bits before that bit as inputs.
Oh, okay.
Right? And then the complexity. Okay, when you look at the document camera, okay, when you look at the document camera, it looks simple because this, okay, traces back to this whole thing here, which is not too complex. But anything that relies on this one here, which is the carry bit of bit 1, is complex because this bit of itself is actually like this big already, right? And yet it feeds into the carry of this bit here. So you can kind of imagine how ugly it can look when you work on bit, okay, I don't even have to go too far, bit 15 is going to be like really ugly already.
Bit 3 is far enough.
Yeah.
Bit 2 actually. Bit 2 was as far as we could get last semester.
Oh, really?
And people were going like, how many terms did you get? Some people end up with like 32 terms because they didn't know how to simplify. So they end up with a lot of terms that did not need to be there.
And that's why you decided, we'll go with 2.
We'll go with 2, but make it structured, make it like stacking. Okay, so I'm hoping this gives you the context of why we are doing this homework assignment, because it is going to be helpful.
Absolutely.
All right, so we are moving on to the lab in about 10 minutes, and that will be room 128.
And you're good. It's software.
It's good to know.